So let's talk about conservation of momentum. How do jellyfish swim? Well, jellyfish swim by changing the momentum of the water. So if we think about, jellyfish being in water, if they shoot out some water this way, that applies a force to them this way, and then they can accelerate. So jellyfish can change their momentum by changing the momentum of the water around it, right? And this has important applications in bioengineering if we think about fluids ever interacting with solid structures. So when fluids interact with solid structures, and those fluids can apply forces to structures. So if we want to ever think about the connection between fluids changing velocity and how they interact with the solid structures that cause the flow to change in some way. If you think about fluids changing velocity in solid structures, this happens all the time in biomechanics. Sometimes if I have some artery that takes a nasty turn, the fluid, as it rounds that bend, applies forces to the walls of the artery. We talked about how jellyfish or any fish swim by pushing on the fluid around them. We can think about rocket ships. Rocket ships shoot out gases at very high speeds out of the back, and that causes them to accelerate as well, right? So if we think about fluids velocities, we might want to think about forces on solid structures. These come up all the time in engineering in general, but also a whole bunch of times, particularly in bioengineering. And any time we want to analyze, hey, what are relationships between forces and fluids, we frame them in the context of fluid mechanics in terms of conservation. We frame this in terms of conservation of momentum. So conservation of momentum is the mechanism by which we can relate forces to changes of velocity in fluids. So the rest of this lecture is going to be a discussion of conservation of momentum. And if we talk about conservation of momentum, we're going to sort of do so in this general framework of conservation of something, right? So if we think about conservation of momentum as conservation of, well, just like anything else, we're going to treat it as a rate balance. So what is the rest of this lecture going to look like? Well, we're going to formulate conservation of momentum as a rate balance. We're going to talk about what's involved in that process, and we're going to go through an example problem at the end to talk about it. So we're going to formulate conservation of momentum as a rate balance. We're going to talk about, what is the left-hand side, what is the right-hand side of all these terms. So at the beginning, we're going to talk about this rate balance qualitatively. What qualitatively are we balancing in this, what terms exist in the conservation of momentum. Then we're going to talk about left-hand side, specific terms on the left-hand side and the right-hand side in a calculus. In a calculus-y sort of way. And then we're going to, at the end, we're going to follow up with an example. We're going to use conservation of momentum in an example problem that helps relate fluids of changing velocity to forces on solid structures. So let's rock. So before I get too deep into this rate balance, balancing rates of momentum, let's take a step back a little bit. Perhaps dust off the physics or dust off the mechanics or biomechanics notes and answer this pose and ponder question. Answer this pause and ponder question for me. The way Newton formed his second law as the following: sum of forces is equal to mass times acceleration. So, did, you know, my pause and ponder, did Newton form his second law this way? Well, it turns out, not really. Not exactly. It turns out that Newton actually formed his second law as the sum of forces is equal to the time derivative of the object's momentum. And it turns out that in some circumstances this is indeed equal to ma. But let's talk about, you know, what is this time derivative of momentum, and perhaps, you know, let's even give ourselves a quick refresher of what momentum, you know, what we mean by momentum. So if I think about the momentum, the linear momentum of a particle, you know, I'm thinking about some chunk. This particle maybe has some mass, maybe it has some velocity. The momentum, linear momentum is equal to the mass of that object times that object's velocity. And because velocity is a vector, linear momentum is also a vector. And it turns out that in a lot of contexts, people use the variable lowercase p to mean momentum. I'm going to have to use it in this case, but I'm sorry, because we use capital P for pressure, but lowercase p with a vector over it is going to be momentum. Spoiler alert, we're not actually going to use linear momentum too much in this class, so, you know, hopefully the p here won't be too confusing. But this is in this context, in the context of just this lecture, p is not going to be pressure, but rather linear momentum here, right? So linear momentum is this quantity here. So if I'm talking about sum of forces being a time derivative of this object's momentum, and we're talking about this object right here, the sum of forces on our object is going to be equal to, as Newton formed it, the time derivative of linear momentum, which is going to be m times v. Well, you know, for most objects, the mass of this object, you know, mass isn't really being created or destroyed in any way. So mass is a constant that can pop right out of that derivative. Then we have mass is equal to dv dt. And of course, the time derivative of velocity we know is our familiar acceleration. So, you know, did Newton formulate his thing as sum of forces equal to ma? Well, you know, kind of. He formulated it as the time derivative of momentum, which, you know, we can say is similar in many ways, you know, which ends up getting the same net result. But the way he formulated it was actually momentum. And it turns out that this idea of a time derivative being, or sum of forces being a time derivative of momentum is actually a slightly more general and useful idea, particularly for fluids. Why is it going to be useful for fluids? Well, in fluids, we don't have this well-framed idea of an object, right? If I'm thinking about a blob of water, you know, a blob of air, a blob of rocket exhaust, there's not really a single well-defined velocity for this cohort of gas, because all of the little bits of gas have all their own different velocities, and there's not really a single well-defined mass, since it's sort of this blob of material. So in this case, I might need to formulate this idea of, you know, F equals ma, you know, there's not really a single object here that's accelerating, I'm going to need to use this sort of more general idea of momentum when I'm talking about fluids. So let's proceed with doing that. So this idea of sum of forces on a single object equaling mass times acceleration of this single object works. But what happens if I had, you know, let's say a whole bunch of objects, all with their own velocities, all with their own individual momenta, could I group them together and instead say, hey, what is the sum of forces on this system? And then in that case, is there a single well-defined acceleration if all of these objects are moving at their own speeds? And then what happens if I say, okay, not some discrete cohort of, some number of particles, but what happens if I'm talking about a fluid where essentially I have, a continuum of material, of chunks all moving in their own separate ways? How can I define, is there a single well-defined acceleration for this cohort of fluids that are all, all these chunks of fluids are, every little bit of fluid has its own velocity. And I could break up this fluid into arbitrarily small chunks and an arbitrary number of them. How do I talk about forces applied to a continuum material instead of a single object? So this idea of a fluid being composed of a whole bunch of chunks, each with their own little velocities, this is going to be the subject of this lecture today. So rather than dealing too much with forces on objects and here this whole bunch of objects, this isn't even super well defined, instead let's take a step back to that more general idea of sum of forces being a time derivative of momentum, or in a sense forces playing a role in the conservation of momentum of a system. So let's talk about forces, and let's formulate momentum as something that can be conserved. So let's formulate momentum as something that is conserved. So what's this going to do? We talked about conservation of momentum. Let's formulate momentum as a rate balance. And first we'll talk about it qualitatively, and then we'll sort of talk about specifically what these terms are in a calculus-y sort of way. So if we formulate momentum that is something that is conserved, we can apply this general conservation principle, the same conservation principle that we did in conservation of mass. So we have a left-hand side, which is a rate of momentum accumulation is going to be equal to the rate of momentum entering our control volume. And we're going to take a control volume approach in the same way that we did for conservation of mass. We're going to do a control volume approach to conservation of momentum. So we have some rate of momentum accumulation in our control volume. Is the rate of momentum accumulating in our control volume is going to be equal to the rate of momentum entering minus the rate of momentum exiting the control volume plus the rate of momentum being generated in our control volume. So we, in the same way that we applied rate of mass accumulation equals rate of mass in minus rate of mass out plus mass generated. Well, we didn't have this for mass, but we might need it here, spoiler alert. Rate of momentum accumulation is going to be equal to rate of momentum in minus rate of momentum out plus rate of momentum being generated. And since momentum is a vector quantity, right? If we dust off our, it's here, right? Linear momentum, mass is a scalar, but momentum, because velocity is a vector, momentum is a vector, momentum essentially has three components. So each of these quantities we expect to actually be vector quantities, and we could equivalently say, hey, this has three components, right? So in a way that we could say, all of these vectors balance out, this relationship is actually a 3-for-1. Hey, did you know that we're going to get a special deal today? 3 equations for the price of 1, right? So we can basically apply conservation of momentum to x momentum, to y momentum, and to z momentum as well. So basically, built into this vector, this equality of vectors, is actually basically saying this is true for x momentum. This is also true for y momentum. And this is also true for z momentum. So this is true, this relationship holds for this, right? So we could basically say this is the rate of, x momentum, y momentum, and z momentum. So this all works. So with this in mind, sometimes when we apply fluid mechanics problems, we might have multiple unknowns that we're trying to solve for. Sometimes the way we resolve multiple unknowns is by applying, by applying conservation of momentum to x and to y, and that way we can get sort of two equations that might help us solve for multiple unknowns. So, so we're going to formulate momentum as something that is conserved, and we're going to formulate this as a conservation law in a very similar way that we did for conservation of mass, right? So it follows this balance of rates qualitatively in the same way that conservation of mass did. So we can formulate. So now we're going to formulate conservation of momentum in a calculusy way that is going to look very similar but slightly modified to the way that we formed a calculusy version of conservation of mass. So let's do the left-hand side first. And so what I'm going to do first is put down conservation of mass. So first, let's do the conservation of mass, left-hand side. And keep in mind, conservation of mass basically had to have units of mass per time, right? It was kilograms per second were all the terms that conservation of mass had to have. So conservation of mass, left-hand side, was a time derivative. It was the rate of the time rate of change of mass in the control volume. And the way we formulated mass was the control volume was an integral over the volume of rho dV. And what did we mean by this? Well, we said, hey, we have some control volume. I'm going to divide up this control volume into a bunch of little chunks. And each little chunk has some volume dV. So the mass of some little chunk is essentially rho dV, right? So the volume of some little chunk is dV. If I multiply volume by density, kilograms per meter cubed times meter cubed, then I get the mass of each little chunk. And then if I integrate all of them, that gives me the mass of all of these little chunks. And if I take its time derivative, that's the time rate of change of the mass of all of these chunks. So the mass of an individual chunk is rho dV. I integrate them to add up the mass of all of the chunks. The time rate of change of that is the derivative of this whole quantity, right? So this is the time rate of change of mass. Time rate of change of mass in our control volume. So let's now compare this to conservation of momentum's left-hand side. And I'll just give the result and then sort of explain how it's similar and how it's different. So it's a conservation of momentum. We anticipate this to be the time rate of change of momentum in our control volume. So in the same way that the left-hand side was time rate of change of mass, the left-hand side is going to be time rate of change of momentum for conservation of momentum. Ready for it? It's d dt, right? So it's still a time rate of change, and it's applied to a control volume in a very similar way to this one. So it's going to be an integral over the control volume. We're still going to divide up our control volume into a bunch of little dV chunks. Only instead of multiplying rho times dV to just get the mass of each little chunk, we still have a rho dV to get the mass of the little chunk. But if you remember, Momentum of a particle is that particle's mass times velocity. So if I think about each of these little chunks having some velocity, the momenta of each of these little chunks is what the mass of the little chunk is times that little chunk's velocity. Well, the mass of the little chunk is rho dv, so if I want the momentum of each little chunk, I just take that and multiply it by velocity, right? So this right here, right, the mass of a chunk, is right here. This is still the mass of a chunk, but the way I go from mass to momentum is just to multiply it by whatever the velocity of that little chunk is. And because velocity could be different for all of the little chunks in the whole control volume, I need to kind of break it up chunk-wise and then add up the momenta of each of those individual chunks. So there we have it. So rho dv is the mass of a chunk. I multiply that by the chunk's velocity to get the momentum of a chunk. So this is a chunk momentum. I integrate it to add up all of the, if I integrate all of the momentum of all, the momenta of all of those little chunks, that's the momentum of the whole control volume, right? By adding up all the momenta of all the little chunks, I get the momentum of the overall control volume, and then its time derivative would be the rate of change of that, right? So the time derivative, the time derivative out front basically makes that a rate of change of all the momentum in the control volume. So it looks very similar. It's basically just plopping in a little v there. And in the same way that, you know, if I multiply mass by velocity, then I get linear momentum, I'm sort of including an extra factor of v in there to give me the momentum, the time rate of change of momentum of all the chunks in my control volume. So that's the left-hand side squared away. Now let's talk about the calculus-y version of the right-hand side of conservation of mass. And in particular, we're going to need to sort of analyze two separate parts of the right-hand side. First, let's talk about ins and outs, and then we'll talk about the generation term. So ins and outs. So ins and outs for momentum. So first, you know, let's kind of keep let's have a control volume at our disposal. And for mass, for conservation of mass, ins minus outs, we had minus an integral over the surface of rho times v dot n dA, where basically I kind of imagined velocities of, you know, fluids going in the surface, and the v dot n basically said, hey, how fast is fluid entering that surface? And the rho basically said, okay, you know, v dot n dA, that's kind of volumetric flow rate through some little segment. If I multiply that by mass, then I get a mass flow rate through that surface. If I take this quantity and put another factor of v, slightly differently, but still a factor of v out front, dA, right? So this quantity, right? So this is a volumetric flow rate. Through one little piece of our control surface. If I multiply that by mass, then this gives me a mass, right? If I multiply this by density, then that converts a volumetric flow rate to a mass flow rate. If I take this mass flow rate, that's kind of the same as what I have here, and I scale it by, and I multiply it by velocity, then this whole thing is essentially like a momentum. It's a momentum flow rate. So conservation of mass, I did this thing to basically, go volumetric flow rate, mass flow rate. If I take a mass flow rate and multiply it by velocity, that's basically a momentum flow rate. So basically what's happening, I have this surface of my control volume. I could have fluid coming in with a lot of momentum and fluid going out with less momentum. And if fluid is going in, if high momentum fluid is going in and low momentum fluid is going out, then there must be momentum kind of changing within the control volume or something else going on as well. So this idea of a momentum flow rate is going to be important in talking about conservation of momentum, ins minus outs. So what do? We sort of started with something similar to mass flow rate. Again, we could do a totally rigorous derivation here, but I think I'd rather build a qualitative understanding of what's going on with this equation rather than bore everyone with a very detailed derivation. So we had something, mass flow rates, which were pretty familiar. We have mass flow rates in and mass flow rates out. That's accounted for this. If we take something that's like a mass flow rate and scale it with velocity, then we get something that's more akin to a momentum flow rate. And if we think about conservation of momentum, conservation of momentum has to essentially be flow rates. If we have flow rates of momentum in, flow rates of momentum out, that's a time rate of change of momentum accumulating in our control volume. So there we have it. And it turns out, and this thing right here basically accounts for both the ins and outs. So if I had some marker, so thus concludes part of our discussion of the right-hand side. So here, like this term here is the ins and outs, but we still haven't really talked about generation. So let's think about what generates momentum. So let's say I had this marker here. If I wanted to generate some momentum for this marker, if I wanted to give it some momentum, what would I do to it? What would I do to this marker to give it some momentum? How do I change the momentum of something? Well, I mean, view this as a pose and ponder, but if I want to change the momentum, I generate momentum or remove momentum of an object by applying forces. So forces generate or remove momentum. If I had a marker and I wanted to change that marker's momentum, I would have to apply a force to it, right? Gravity applies a force. If I take this marker and let it go, gravity changed the momentum of that marker by applying forces to it. So forces generate or remove momentum, and in particular, it's net forces on an object or on a system or whatever generate or remove momentum within that object or system. And so this rate of momentum generation in our control volume is essentially what I'll say, so the rate of momentum, generation is a vector quantity, because momentum is a vector, is equal to the sum of external forces on our control volume. So if I have external forces on our control volume, it's these external forces that are responsible for generating or removing momentum in this control volume. So if I have some control volume right here and I apply some external forces to that control volume, it's those external forces that are responsible potentially for an imbalance of ins and outs or a time rate of change of momentum in the control volume. So it's these external forces that are the momentum generators or removers. So before we get too deep, I've talked about a whole bunch of terms. Let's put it all together. Let's put all of our terms together. So the left-hand side was d dt of an integral over the volume of v times rho dv. And this is equal to minus an integral over the surface of vector velocity times density times v dot n dA plus the sum of forces external on the control volume. Anytime we get to a result like this or are trying to analyze equations or things like that, before we get too far, let's think about units. And I guess this isn't really a derivation per se or a problem that we're trying to solve, but let's think about units. So I pose to you, as a pose and ponder, let's work out the units of all of these terms. So pose, ponder, what are the units of each of the terms? Each of the variables, even within these expressions, do they all match up to have the same overall units? All right, so hopefully you've paused and pondered. If I think about it, sum of forces, well, forces, if we're dealing with SI units, those have gotta be in newtons. dA, area, is going to be meters squared. V dot n, well, n is unitless since it's a unit vector. V dot n is going to have units of meters per second. Rho has units of kilograms. It's density, right? It has units of kilogram per meter cubed. And V has meters per second. If I want to square away some of all of these units, I get meters, meters, meters. So I get meters to the fourth over meters to the fourth kilograms per second squared. Oh, and I have a meters cubed in the denominator. So I can simplify this just a little bit. The meters to the fourth goes away and the meters cubed. So what am I left with? I'm left with kilogram meter per second squared. Is that familiar? Heck yeah. Heck yeah. Kilogram meter per second squared. Oh, that's the same as a Newton. Whew. And good thing too, because baby you know who would get very upset if these two terms had different units. So forces are kind of equivalent in units to momentum, rates of momentum in and rates of momentum out. So one last little bit. Let's make sure the left-hand side still has the same. So dV, that's a volume. That's going to have meters cubed. Rho is kilograms per meter cubed. And V is meters per second. And then if I take the time derivative of this term here, I'm going to get 1 over seconds, right? If I have some quantity and I take its time derivative, then it's that quantity per time. So that's why I get 1 over seconds from the ddt out front. So all these meters cubed and meters cubed cancel, and I get kilogram meter per second squared, which also equals newtons. So newtons, 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 all the way home. Great. So so all of these things, in some ways we could interpret them as, some of these things are forces. Forces are time rates of change of momenta. So in a sense, all of these units, all of these terms in this conservation of momentum equation need to be rates of momentum or forces, both of which end up having units of Newton. In a lot of fluid mechanics problems, it's not necessarily the concepts that are often the hardest part, but the bookkeeping. So I'm going to offer some tips on how to do the bookkeeping for these forces right. And in particular, the forces can be problematic. The key thing here is if we're talking about external forces, right? So if we're talking about external forces, sometimes people get tripped up by including internal forces and kind of, in a sense, like double counting things, or having internal forces that they've put in here, when this sum of forces should really be external forces, right? Because if I have particles that are both, if I have two particles within my control volume that are applying forces to each other, that's something entirely internal to my system, right? So if I, they're not, even if they're applying forces to one another, they're not changing the overall momentum of the system. It's only external forces that can change momentum of this system. Right, so here are some tips, some bookkeeping tips on how to make sure we include only forces that are external, and also make sure that we include all of the external forces, that we don't miss some or double count some. So let's talk about how we do that. So let's think about these external forces, and these external forces come to you in 4 flavors. So these 4, so by what means can we apply external forces to a control volume? Well, there are essentially 4 means that we can apply forces to a control volume. So let's hash them out here. What are the 4 ways that we can apply forces to a control volume? So 1, I can apply shear stress on the surface of a control volume. Right, so we talked about this a little bit in some of the example problems when we were talking about velocity gradients in Newtonian fluids and viscosity and things like that. We said, hey, I have maybe some plate that's moving at some velocity. If I wanted to define a control volume, let's say as this chunk of fluid right here, there could hypothetically be some shear stress on this surface here, right? There can be shear stress that tugs along. If shear stress is pulling in this way, I guess this is a sort of negative shear stress if we're using our positive convention in the other way. Whatever. Don't worry too much about the convention, but shear stress can tug on the surfaces of fluids, and the way I go from a shear stress, the way I essentially go from a shear stress to a force is by multiplying that shear stress by area, or if that shear stress is variable, integrating that shear stress over the surface. So, a force due to shear stress is equal to stress times an area if stress is constant, or I need to integrate tau dA over the surface to get some overall force, right? So if shear stress is variable, I'm going to need to integrate it. If shear stress is a constant, I can just multiply it by area in order to get the force due to that shear stress. So shear stress can apply forces, external forces, to my control volume. If there's shear stress at the surface, that's putting a force on this fluid. So what are some other ways that that I can apply force to this to a control volume? Well, pressure. Another one is pressure. Pressure can apply forces to a control volume. So let's say I had a pipe, and I wanted to push fluid through that pipe. Well, if I define my control volume to sort of be, let's say, just on the inside of this pipe right here, a lot of times if I'm flowing through fluid through pipes, I'm going to need a higher upstream pressure than downstream pressure in the pipe in order to push that fluid through the pipe. So what's that going to look like? I might have a lot of pressure. Remember, again, pressure is defined as pushing inwards. I might have a lot of pressure upstream and a little bit of pressure downstream. So if I want to talk about force of pressure, it depends on whether pressure is uniform or not. If pressure is uniform, I can just multiply pressure times area. If pressure is non-uniform, then I'm going to need to integrate pressure over that surface. And by knowing that pressure acts inward on a surface and perpendicular to that surface, we can get the direction of the force associated with that. What are some other ways that we can get external forces on chunks of fluid? Well, gravity. Gravity can apply forces to fluids, right? So let's say instead of having this pipe be horizontal, if I had some vertical pipe, with the control volume drawn just barely inside of it, gravity is tugging down on the whole volume of this fluid, right? Fluid has mass. Gravity pulls on things that have mass. So gravity's tugging downwards on every little chunk of fluid in this control volume. And you can formulate it, in a couple of ways. If you sort of have a homogeneous fluid throughout this whole thing, then the force of gravity is basically going to be density times the volume of our control volume times g, right? And it's going to be acting downwards. Or if we have, for example, like some variable density within our control volume, then you would sort of need to integrate rho g dv in order to get the overall gravitational force. And again, it would be pointing downwards, so you got to worry about the direction as well. And then the final way that we can apply forces to a control volume is if our control volume surface, or the surface of our control volume, cuts through a solid, right? So here, shear stress, pressure, and gravity, these are all things that are essentially acting on fluids, right? Pressure can act on the surface of a fluid. I mean, pressure can also act on the surface of a solid too, but, these are all things that can act directly on the fluid. But sometimes, let's say I had, some like a little airplane wing or some kind of goofy structure here. If I were shooting some fluid into one side and that fluid got directed upwards like this, if I drew my control volume kind of looking like this, in this way I have x momentum entering my control volume, but because this is redirecting that fluids upward, I have less x momentum exiting than entering, right? So in this case I have lots of x momentum, right? If you think about each of these barrel things, and here I have less x momentum exiting than I had x momentum entering. So what's accounting for this loss of momentum? Well, I'm basically going to need to be applying some force to this control volume. And if my control volume cuts through this solid here, basically I'm going to need to apply some force to this solid structure here. I'm going to need to apply some force, and perhaps I might need x and y components as well, but it's the forces that are applied essentially through this solid material that result in the momentum change here. Strictly speaking, is there pressure and shear stress all the way along this surface? Yes, but if my control volume fully surrounds that interface between the fluid and solid, then any shear stress or pressure that's interfacing between the fluid and solid, all of this stuff is internal, right? So this is all internal and shouldn't be included in my sum of external forces. But if my control surface cuts through part of this solid structure here, those external forces can be transmitted through that solid right here. So these are basically the 4 ways that we can get external forces on our control volume. All right, so now we have a sort of formalized structure, right? We have a way to kind of deal with all of these things. Now would, of course, be a great time to do an example problem where I could bring it all together, but it's past my bedtime. So I'm actually going to hold off on doing the example problem and include it in the next lecture. Sorry to promise something and not deliver on it, but stay tuned for an example problem on how to use conservation of momentum. All right, so thanks for listening, and good luck with your studies of fluid mechanics. Cheers.